Yes, the engineers are here. Kinematics, the geometry of motion. So, had a quick conversation or two actually with Evald yesterday. Just these questions are weird. Let's see, which one was that we were looking at? 26. I think 26. Anytime they give you some equation and then they say it's linear motion, that's really it's really confusing. Like you almost want to make a table like I did in class as opposed to drawing a graph of it. Because if you draw the graph of a cubed equation, it makes you think, oh, that means this thing is flying along this cubed equation. I think it was 26 Evel and I were talking about. But yeah, there's some tricky questions in here. You're not going to see a question like that on the test. You might see an erratic motion problem on the test like that mountain biker that we did in class at the end last time. That's a good question. But always be ready to start every class with questions that you had from the homework because there's some tricky stuff. So that being said, I will expect you to interrupt. So really what we did last time was all linear motion. You were given complicated equations that describe linear motion. And today we're going to look at stuff that isn't linear, like number one, stuff that's projectile, flying through the air just under the weight of gravity, which I hope isn't totally new to you. And then two, something you may have looked at a little bit in physics, but curved motion. And so straight line motion is kind of like, why would something go straight? Now, there's examples like piston in a car is just going to go back and forth and so forth. So it's not as though that doesn't exist, but in terms of seeing an animal run down the road or, whatever there, it's like they're going to curve around. And so we need to be able to handle both. Dynamics is all about motion. We are looking specifically right now in chapter 12 at the geometry of motion, not what causes the forces that cause that motion to happen. We're just looking at what does it do flying through the air. So this question is really a 12.6 question. So this is getting you ready for the questions in your assignment 95 through 107. Really one question I think may do it. But let's see what we can come up with here. So here's this mountain biker. And I just did this yesterday. And the goal of the mountain biker going down this jump right here would be to leave at this point O and fly according to that dotted line. I don't know if it makes sense to you, but if you flew a little too slowly and landed like that, does it make sense that impact is going to be really hard? You're going to smash that, come to a stop, and you're not going to have near as much fun. So being able to figure out what velocity I need to take off at to follow that all the way down and land down there somewhere, you may be able to see that if you landed kind of anywhere along here, you'd be okay. But the main thing is the goal in this problem, if you will, is to take off sort of 4 feet above the landing zone. In other words, it's kind of like you went out there and took measurements and said, I'm 4 feet higher than where I'd like to land, and I'm also going to fly horizontally through the air 12 feet. If I can land there, that'd be great. That's what you're saying ahead of time. And so if the jump is asking you, or forcing you, maybe I should say, the jump is forcing you to take off at 32 degrees, you're stuck with that thanks to the jump maker, then only thing I really have is velocity. So we want to know the velocity and the time for this mountain biker to leave the double at O and land at L. And we don't need to know anything that we don't already know to figure this out. So let's see if we can wade in and do that. Do you feel like you understand the question?
Yep. Out of curiosity, are we gonna like do this by just breaking up into how the vertical velocity is gonna change with gravity, and then just like set the horizontal velocity to constant?
Exactly right. So what you should know from physics and also from Math 112, if you got a chance to mess around with this a little bit before, because again, I'm hoping this really isn't new, is that the horizontal and vertical act independently here. So in other words, that V0, which is your actual vector velocity stuck at 32 degrees, is really Pythagorean theorem between V initial, and that little O means initial velocity at O. You got the Y direction, or you got the Y version of that. So you're actually kicked up in the air a little bit. And then you also have your X version, and those act independently because ultimately gravity pulls on the Y direction, but it has no effect on the X. So one of the things I could figure out right now is I could say, and really, V0 there is actually kind of located at the hypotenuse. It is that vector. So if I say, hey, that V0x is a cosine problem. So if I say the cosine of 32 equals adjacent over hypotenuse, then that means that V0 in the x is just the original velocity, but modified by the cosine of 32. Isn't that what we've been doing all last term? We modify that by the cosine of 32, and that gives us our horizontal component. And the key is really that's just constant, like that never changes. Now, practically, it changes a little bit because of wind resistance and friction. If you're sort of flying through the air like a sail, then you're catching wind, then you would actually be slowing down because of friction. So, in this short of a distance, does it make sense? That's going to have very little effect, though. It's not that it isn't real, but in this application, I'm only going to be in the air for like 1 second or maybe even less. And it seems like maybe that wouldn't be going all that fast. And so I'm going to kind of note that this is constant. And again, we're having a conversation. This isn't a monologue, so weigh in on your opinions on that as well. And so similarly, it would also be true that V0 of y would be the same thing, except for it would be modified with the sine of 32. So I've got those two facts, and I get to deal with those independently. And now is where your position equations come in, because notice this whole problem is kind of pertaining to position. In other words, I'm at position O and I want to land at position L. And so if I bust out my position equations from last time, I'm just stealing this straight off of the dynamics note page that I gave you. That S. And let's consider both of these, I don't know, independently. So let's switch colors. Let's say one here and say this is position. So let's think about all of these positions. Now watch this carefully, but remember from before, position is 1/2 times acceleration times time squared plus the initial velocity times time plus the initial position. That was our equation. But we want to do this independently. So for x, this would be your position in x. This would be the acceleration in x. This would be the initial position in x. And this would be the velocity in x. I guess I can just leave it that way. So I'm only considering x. And now let's just think about what do we know as a result of that? Well, don't we know? Again, it kind of depends on what we call zero. So I'm going to say position with O at the origin. So you have to decide where the XY axis is. I'm considering it to be right here. It doesn't matter where you put it. You can put it anywhere, but that makes the most sense. That's the starting point, right? So I'm going to put it right there. It wouldn't be a terrible idea to put it down here. Matter of fact, I think I'm going to change my mind. That actually seems like a good idea. So I'm going to put the origin right there. So let's see, just to have it labeled, I guess I'll just call that for no good reason. A is the origin, point A. So if that's true, what is my initial position? My initial position is 0 because I'm sort of starting here at O. That's where I am right now. So in the X direction, I'm nowhere. I'm right above it. Now I'm 4 above it in the Y direction, but that's why. And would you agree that your initial velocity in X, we just figured out a second ago, was the initial velocity times the cosine of 32? And then what about this last term, the acceleration? What's the acceleration? If you're flying through the air in the X direction, based on this statement right here, the fact that I said that velocity in X is constant, what's your acceleration? What's accelerating your motion through the air?
Nothing.
Nothing. It does. Your speed isn't changed. There's nothing acting on you that would cause you to slow down or speed up. Again, we're saying if wind resistance is negligible for the tiny amount of time we're in the air. So notice everything sort of goes away then. So we can just say that S of X is just equal to V0 times the cosine of 32 degrees times time. Again, I kind of want to note that because that's an important equation. Notice, okay, great. And if you want to learn to think like a mathematician, the best thing is to say, hey, I got this equation with 3 unknowns. So let's see, if I knew 2 of them, then I would know the third one, but I don't know any of those right now. I'm just kind of trying to build stuff right now. I don't really know what I'm doing. I'm just kind of writing down. I'm using all these equations, just kind of writing down what I have. I'm not doing this because this is step 1. I'm just doing this because, well, those formulas exist. Those are things I know, right? So I have an expression for the velocity in X and the velocity in Y. And then I'm thinking, well, position, because this thing is flying through the air. So now let's do this again, except for let's do this for Y. So the position in Y, since they act independently, would be the acceleration in Y times time squared plus V0 except in the Y direction, and the initial position in Y. What do I know about that? Well, based on where I chose the origin, does it make sense your initial position in Y is 4? Had I chose the origin up at O, then that would also be 0. And maybe that's an argument to change it, but I'm not going to change it now. And just like we did before, we would say that the initial position in Y could be changed to V0 times the sine of 32. And the only reason that's good is because notice both of these equations I'm making right now just have one V in them. They don't have 2 different V's. V initial velocity in X, initial velocity in Y. I just replaced them so they both have the same exact unit. What about the acceleration in Y?
Well, we got gravity.
Gravity. So you would just fly forever, except for we got gravity. Now in this problem, what's the constant of gravity based on the units that you see?
Isn't it negative 32?
That's exactly right. So in feet, in metric at the start of this book, and we used it a little bit last term, in metric, we said, this book said use 9.81, not 9.8, but 9.81. And for feet for the kind of the standard system, it's 32, except for in this book, it says go a little more accurate, use 32.2. And so this gets replaced with, and it's negative. Why is it negative?
It's going toward the, presumably toward the center of the Earth, which is down.
Down. That's
With the
exactly
system we have. Yeah.
right. Yeah, gravity's pulling you down. That's exactly right. So that doesn't go away this time. And so let's see, what do I have for my y equation then? I've got half of 32.2, which is 16.1 t squared plus v0 sine of 32 t plus 4. So there's my S equation. Notice it also has three unknowns, S of y, t, and v0. And so these equations govern the flight of this in terms of its position. So I know about its speed. Interesting. But again, I'm just kind of overrun with unknowns here. So what do I do? Also think about, let's see. So there's kind of some position equations. I don't like that. I'm going to need more room. Where did you come from? I don't want you there. So I also need, besides, so remember there's three components of motion. There's acceleration, and in this problem, because it's projectile motion, there's no acceleration horizontally to something that's flying through the air. Nothing is propelling it forward or backward. But vertically you do, and it's gravity, so it's constant. So there's the constant 0. If you're traveling horizontal, the constant is negative 32.2 or negative 9.81 for metric. That's the constant acceleration. And so we have a position equation, and then we need a velocity equation. So let's write that out as well. I think I'm going to rewrite this smaller since I can see I'm going to run out of room. S of y equals negative 16. I want you to think about that though. What would the velocity equation look like? Or did I already write them? Did I already write the velocity equations? Well, what's your velocity equation? Again, if I look at the sheet, we from calculus made the velocity equation, and it was velocity equals acceleration times time plus the initial velocity. Isn't it the general? That's the general velocity equation. So what's the velocity in x? Well, since in x there is no acceleration, then the velocity will just always be whatever it was. And so we did already make this equation. So I'll say since a equals 0. So there's our velocity in x equation. It'll just always be whatever the initial velocity was. Remember, we don't know what it was in this case. So there's kind of my x equation. What about my y equation? Well, isn't it also velocity in y equals acceleration times time, negative 32.2 times time, plus its initial velocity, which we said was v0 times the sine of 32 degrees. It's a little confusing here that, that says v0, initial velocity. really that would be v0x or v0y for us. So in the y direction, the velocity is actually changing. It is not going to stay whatever it started out as. It's going to get reduced every second by 32.2. And so, great, I sort of have then all of the equations I could possibly make. And it might have been good to state up at the top that acceleration in x is equal to 0, whereas acceleration in y is a constant. I mean, those are things I could have stated too from the start. We used them, but I could have written them down. So the point is, all I'm doing is just considering all the different aspects of motion. Now, I'm not inordinately happy with this because I just feel like I have unknowns everywhere. And what I'm really staring at is just these 4 equations here. Those are my tools to work with. What can I do? Can I do anything? What are your thoughts? I just feel like I have all these equations. Can I use any of them? Can I know anything? It just feels like they're overrun with unknowns. So do you understand that these equations model its position anywhere? But what am I considering? What do I really know here? Well, the only thing I really know is this. I know I would like to land there. That's the one known that I haven't got involved here. So I'm flying through the air, but I don't know what speed to leave at. The only thing I know is I'd like to land out at that point. Well, based on where I chose the axis, I'd like to land out at the point 12, 0. So the x distance I'd like to be 12, and the y distance I'd like to be 0. Well, maybe we should start there then. If I take these 2 equations, so I think at 12, 0, then I say, well, s of x is 12. So that means 12 would have to be equal to v0 cosine of 32t. I'm not super happy with that because it's got 2 unknowns in it. So I can't solve anything there. I'm not super happy with the s of y equation because when the y distance is 0 again, remember it started at 4, when it gets down to 0, then I've got, well, everything else filled in, negative t squared plus scoot you over plus v0 sine of 32 plus 4. I'm not happy with that either because it also has 2 unknowns. But if you're good at math, what are you happy about there?
We have a system of equations.
Yeah, I forgot the t there. I'm squeezing it in. We have 2 equations, 2 unknowns. So I'm not happy when I have v0 and t, but if I have another equation with v0 and t, suddenly I am happy. Yeah, I can solve that, which means I'm going to be able to find t and v0. Isn't that kind of cool? That means we're going to be able to find the time and the velocity, the initial velocity. So we actually just allowed the mountain biker to pre-calculate that. Also, we know how long we're going to be in the air. I would assume if you're an X Games person, it's like, do I have time to do a 360? Do I have time to do a flip? Remember, you're going to fly through the air as a particle, like as a center of mass, but you're more than welcome to do whatever you want up there while you're flying. You can throw your bike around over the top of your head, spin around, do a twist, kick the wheel out and come back in. Well, it'd be nice to know how much time you have. If I have 30 seconds, maybe I could do all kinds of cool tricks. So do you see how practical and how kind of cool this is? How are you going to solve that system? What's the easiest way to solve this system?
Pop in a calculator and see where the lines intersect.
Exactly. Nice answer, Daniel. Just graph those 2 things. Graph them in Desmos. and just let them run into each other, cheat. I think in the interest of time, I am going to do that, which isn't usually my shtick, but I will say if you solve the top equation for V0 and substitute it into the bottom one, this solves algebraically pretty nicely too. It's kind of neat because it actually has a squared equation for t, which gives you two different answers to this problem. And that's because there's two different times on this parabola up here. There's two different times when it'd be at 0. But the other one, if the parabola continued, would be over there at a negative distance. And so we sort of don't have, it'd be like back in time, like 2 seconds ago, we used to be over there, so to speak. But since we're on this, double jump, we never were there. So we would only be interested in one of those two answers. But let's highlight this. This system in Desmos. I'll tell you the answer now, and then we'll just cruise on. Well, maybe we'll go take a quick look at it, but I end up with t is approximately 0.845 seconds. And I get V0 is approximately 16.7. What would its units be? Based on our units that we're working with here, we were stuck in feet. So we know that feet is the length unit. Do we know the time is seconds? The answer is yes. Does anybody know why?
What else can you measure time in?
Minutes, hours, weeks.
Well, I mean, yeah. But you also
Because of our
did prove the
acceleration,
right
right?
seconds.
Because we called the acceleration of gravity 32, that's 32 feet per second. So that's where the seconds come from. Otherwise, and it'd be dumb. Obviously, we're flying through the air. You're not going to measure that in months or something. But the units do follow, I guess is what I'm saying. So we wouldn't have known 32 unless we chose the time unit, if you will. And so that isn't obvious. So this would be feet per second. So that's kind of cool. I mean, do you see the power of this? Like, this is a pretty hard question, but it's pretty interesting to me because I do this. I jump stuff like this, and I'm too old to crash. So this tells me, hey, if I cruise up to this jump at 16.7 feet per second, which means I actually could look at a speedometer on my bike and look down and pedal harder if I needed to, that I would land in the right spot. And I can see now that that's going to take less than a second. So that's kind of cool to know. I'm not going to be flying very long. It's amazing. It's really cool that you can figure this out. I mean, that's an interesting problem. The typical physics problem, they actually give you the initial velocity and then say, where are you going to land? But notice mathematically, it's much harder, but much more practical to actually use these equations to go in a completely different direction. So that's kind of cool. In the end, I guess I didn't even need, and this is a good example of kind of how you should think about algebra, in my opinion, is I didn't need to do this. Do you see that now? I guess I never needed those equations for anything. I didn't know what I was going to need, so I just figured out everything that I could figure out and then just started playing around with it. Really powerful. This is something you definitely want to understand. So engineers would never figure this out. The mathematician in you should recoil at cheating to answer this, but engineers are just trying not to screw up. So even if you knew the math really well, it's dangerous to kind of trust yourself. You should trust yourself if you love math, but check it too. Make sure it works. So let's answer the second question because this is kind of cool too. At what angle and velocity does he land? Why would you care what angle and velocity you're going to land at here?
Because if you land too fast or at a bad angle, you're going to die.
Exactly. If I land really fast there, like there could be a corner coming up or something of that nature, you might feel out of control. Obviously, this is a fairly small jump, but you know, people in X Games, they're jumping huge stuff. And so, you know, how fast am I going when I land? And what angle? Why does what angle matter? Does it make sense? It'd be really cool to actually land like this, to come in and land tangent to the curve, land right there. Does it make sense you wouldn't even feel that? I've landed stuff like this, and then the bike bounces down, and then I fly up in the air and fly off the bike and land in the rocks. And so the more this angle right here, the smaller that angle is right there, the more smooth your landing is going to feel. Like based on this drawing, you're probably not going to crash as a result of the land. But obviously, if the ground was like this instead, then that angle's now really big, and that's when you're going to kind of go smack and absorb it, you know, mostly with your arms or maybe with the bike and so forth. So this is kind of a cool problem. So how am I going to find that out? Well, it asked about velocity. Do I know anything about velocity? Yeah, I have these two equations. Don't I know everything I need to know to figure those two out? So because I asked a second question, I guess I do need these two. So I found physics very hard because it always seemed like the teacher knew exactly which equations to grab. And I found myself not knowing that. I would always like, how did you know to grab that when there's like 500 equations? How am I supposed to know which one to grab? But you know, the problem said, hey, what's the velocity? And I think, well, do I have any velocity equations? Yeah. Had I not just randomly made them earlier because I was curious, I would have to go make them now. But don't I now know that the initial velocity we said was 16.7, so v of x equals 16.7 times the cosine of 32, which of course is easy. I already calculated this out once, so I won't do it again. So velocity of x is 14.2 feet per second. That's not my actual velocity, but it's my velocity in the x direction. It's the velocity I took off at, and it's still the velocity 12 feet later or 0.8 seconds later. That hasn't changed. But the velocity in the y direction definitely will change because time is elapsing. And notice I know the time is 0.845 seconds. I think that was it, 845. So that's t plus the initial velocity, 16.7 times the sine of 32. And by the way, I forgot to mention this, but notice that initial velocity is up here. It's positive. It isn't always positive, but it was in this case. So if I crunch all of that together, I get the initial velocity or the final velocity in y. You should be able to tell from the picture, is this velocity going to be positive or negative? Well, he's flying downwards, so it's certainly going to be negative. So there's my velocity in y. Now, in one sense, I could say, I'm done. I know my velocity in y and x separately. But think about what that means. Those are kind of vectors, aren't they? So it's kind of like you have 14.2 going this way and slightly longer than that. going this way. Notice I'm aiming it downward, but I'm just going to call it a positive number. So we did this a bunch in statics. Couldn't I use Pythagorean theorem to find your actual velocity through the air if I wanted to also know that? And then wouldn't that allow me to find this angle relative to horizontal if I wanted to? So I could say the tangent of theta equals opposite over adjacent, and that gives me an angle, again, relative to the horizontal of about 52 degrees. So if I knew the angle that the land was at, if you will, then I would know, because what I'm really interested in is the actual sliver right there. But the point is I know that that angle right there is 52 degrees. Let's see, not that angle, this angle. I know that angle is 52 degrees. So that's kind of cool. And then, of course, I could Pythagorean theorem to find my actual velocity, which would be 14.2 squared plus 18.4 squared. So that final velocity is 23.2. And notice in the real world, you probably would not put a negative number on that or positive. It's just like, how fast am I flying? So I have the magnitude of my velocity, and I even have the direction, magnitude and direction. That's what vectors have, is both a magnitude and a direction. So armed with all of that, I could say this is, vector v if I wanted to. But the magnitude of vector v, really this is a magnitude statement, is 23. So cool. I know how fast I need to take off. And not only that, I know how long I'm going to be in the air. I know what angle I'm going to land at, and I know how fast I'll be going. And then I can decide, is that all right? Like, will my legs, will my shocks be able to withstand all of that? Really cool problem. So you just have to be creative, I guess, is what it comes down to with this. It just depends on what you're being asked. Again, I asked a harder question here by not giving us our initial velocity. But again, I think that's so much more practical, because if I'm in the X Games and I'm jumping some really big jump, I'm not just going to go up to it and say, hey, I think I'll go 40 miles an hour. I mean, what I really know, I know where I'd like to land, and I'd like to figure out what velocity I should go, not just pick one and then hope for the best. So in a sense, I gave you a more practical and simultaneously kind of a harder question. So my advice on that is to, I don't know, kind of study this carefully. In a sense, what I would say, the biggest knowledge I imparted to you here is just to produce these equations, the three components of motion anywhere. Doesn't matter whether you're flying on a straight line or you're on the ground. The three components of motion are position, speed, and acceleration, or position, velocity, and acceleration. And you have equations for those. So write them all down. Just write them all down, and then stare at what you got. And then look at, what do you know? What do you know? What do you want to know? In this case, it would have been easy for me to get stuck here, not realizing, hey, I know something. I know I'm supposed to land at the point 12.0. And so that's what allowed me to proceed. Otherwise, I would have sat there staring at these big equations with a whole bunch of letters and not really knowing what to do. But once I plugged that in, all of a sudden I did know what to do. So you're never going to understand this if you need someone to tell you steps. I need steps for this. 1, 2, 3, 4, 8, 9, 10, 11, 12. There's too many of them. Always just write out all of the equations that you have and plug in things that you know. Notice I didn't know, even though I had these two equations written down, I didn't know anything about those. I didn't know time. I didn't know initial velocity. So it's like The one thing that I did know is something about position, and that's why these equations weren't helpful and turned out not to be even necessary to start with. I did know something about position, which is why I ended up being able to do something with these position equations. How do you guys feel about that? Do you find yourself tracking with that? Do you find yourself thinking, okay, I've got, what is there, like 4 assignment questions here? Do you feel like you're going to be able to get them right based on this discussion?
I think so, because like it's also pretty easy to like guess and check if you get desperate
Nice
to
job.
like check your work.
Nice job. Guess an initial speed, and then do the calculations where you have more knowns. So I would really agree with that statement, Daniel. That's a good one. How do you feel about this, Evel?
I'm feeling the same way, pretty much.
How about you, Landon?
Yeah, I kind of feel like I might have to remind myself to actually go to the equations I already know instead of just trying to work through it based on what I know about velocity and acceleration.
Yeah. Notice all that really changed here from yesterday is that we had some accelerations built in. It's the same set of equations, but we have no x acceleration and we do have a constant y acceleration. And so that's what essentially inserted itself into our problems. So with no a acceleration, then velocity in and velocity out were identical for x. So in a sense, the a of t was nowhere to be found in this equation, but it did exist down here. So these are just the equations we used before, and yet it still applies because you can look at, just like we did last term in statics, you can look at x and y independently. Gravity pulls on anything independently of whether it's flying forward or not. So anyway, pour over this example, ask me questions in your homework, but really go slow with that. Okay, now we're going to look at an example involving not straight line motion, not parabolic motion. It turns out you fly through the air in the shape of a parabola. Notice you never had to know that here. Like we never even knew that was the case. It's actually calculus that created the squared equation that causes this to fly in the shape of a parabola. It's not like I had to tell you it flies parabolically. Did you notice that? We never even discussed that. But the squared aspect of time, because you're taking an integral velocity to get acceleration, that squared time is actually what caused it to fly in the shape of a parabola. So now what we're going to look at, stop sharing. This is really cool. And actually, I'm not sure if you discussed this in physics or not. But we're going to look at something here called curved motion. Now notice this red path right here is totally random. Notice we're not moving in a straight line. We're not moving in a nice organized parabola. This is like somebody just made a road of a random curves. So the curve comes along here. Let's turn this off for a second. So you can drive along this road. Boom, I'm driving along this road. And when you hit curves, you know, it's not like you're looking at those thinking, you know, hey, this is a circle, or, oh, this is a parabola. You're just kind of cruising along that section of the road. But here's the brilliant concept of this. Let me open up another drawing here to help you understand this. So I chose a path here. So again, it's red. So think of yourself as driving along this red road. And then you get down here and you kind of take a sharp corner and then you head back off into space again. It turns out, and this is amazing, it turns out that at least where you are right here, your position right here, for that instant in time, Does it make sense? The little chunk of red curve right here can be thought of as being a circle of a certain radius. In other words, you're traveling on a circle, and that blue circle is the circle. There's the center of the circle, and there's the giant circle. And so at least for a second, you notice how closely that circle is an exact match to the parabola? Now, does it stay exactly the same? No. See how it starts to depart down here? Because that red curve is random. In this case, it's the parabola, but in the real world, it's random. So, but the point is if you're curving, at least for a little tiny chunk in time, thanks to calculus, you can think of that as a circle. And so you see how good of a model that is? It's perfect, actually. I mean, when you get right in here, I mean, at least for this period of time right here, the circle and the parabola are identical. Now, what's going to happen to that circle, though, if you move down here? I want you to notice what the radius of that circle is, because I made a Desmos formula to show you this. Notice that radius is roughly 13. What's going to happen if you move down here, though?
Should shrink. It should shrink, right?
Yeah, you're exactly right. Notice if you move down here, you see how the circle's getting smaller? Well, of course it is, because the curve is tighter right there. Notice down there, the circle is a radius of only 7. And yet if you get in really close, notice again, the circle is a perfect match. But see, the circle just changes all the time. Does that make sense? 1 second later, totally different circle. But the cool thing is we know a lot about circles. That's kind of the idea. So you're always traveling on a circle. That's kind of what it comes down. It's just that the circle's constantly changing. And so notice when you're right here at the bottom, that's the sharpest place you are. Notice the radius there is like 5. That's like the smallest, tightest part of the curve, if you will. If you're driving the car, that's the sharpest corner of the car. Do you also notice in that orange line that I have down here that this side right here would be where your headlights are aiming? Does it make sense? You're always aiming tangent to the curve. Your lights are going to be pointing out tangent to the curve at any given time. So again, think of that orange line as like your headlights. That's the direction you're going. Notice also the radius is perpendicular to that. So at any place you are, your direction of aim is perpendicular, but the center of the circle on which you are driving, if you will, is perpendicular to that. And so in a sense, you're, at least for that instant in time, you're sort of traveling around this point right here. You see the logic in that? Now, before we leave this, notice the equation that I have over here that calculates the radius for you. See how it says 1 plus the derivative squared, and then that whole thing is in parentheses, and then it's raised to the 3/2 or 1.5 power, and then that's divided by the second derivative. Like, that's the formula that will actually tell you the radius. Isn't that cool? So like I'm on a parabola here, and I want to know what's the radius of the circle I'm on right now, like at the point I'm at. Remember, it changes, but right now I'm at the point, well, I'm at the point 7x is 7.82. That's where I am right now. And right there, the radius is 13.39. So notice you can find it based on the derivative of the actual equation that you happen to be driving on. So if there's a parabola, as there is in this case, if there's a parabola sitting there, then by taking its derivative and squaring it, you should recognize 1 plus the derivative squared. Remember that is arc length from calculus. That was a while ago. That's arc length. And then you're dividing by the second derivative of that same exact equation, but with, again, whatever point you're plugged in at. And so you can actually find the radius according to that circle. Do you have a copy of my note sheet? I'll pull this up in a second perhaps, but that's one of the formulas that we need for this section is how do I find the radius? So let's just play around with this a little bit and let me help you kind of think some things through. By the way, is that utterly new to you, or did you talk about that some in physics? Because I've spent so long since I took physics, I have no idea what the answer to that question is.
We talked about that stuff a bit. Though I don't remember exactly what we did. The only thing I remember from that part was Dusty talking about how he had a friend who had this car that could only go 50 miles per hour, but it could take any turn at 50 miles per hour. So they try to go double the speed limit for any turn. So if it's 20, they go 40 on it.
Mhm.
And he was explaining how like if you go double the speed, there's 4 times the force pushing inwards and stuff.
Yeah, interesting.
Only thing I remember from first term physics.
So, yeah, and we're going to talk about that right now. So, what we're talking about now is not motion that is a parabola, not parabolic or projectile motion, but just curved. Notice that isn't even defined. It's just like not a straight line. Now you're just curving. So let's just play with this for a second. Let me help you understand the implications of this. So let's say you're on this road right here. Notice it's not very curved, if you will. Notice that's a pretty mellow curve. I haven't shared my screen. You can't see anything. Just a second. So let's say you are right here. So you're right here. That's where you are. Well, let's see. Notice based on the curvature, would you agree the center of the circle looks like it's maybe right there? I'm just kind of guessing. So this distance right here in your book is described as not r for radius, but the Greek letter rho, which kind of looks something like that. So it's spelled R-H-O. And I sort of wish this wasn't, kind of looks like a P. I'm not sure why not just use R? I mean, frankly, I would just use R for radius, but the book doesn't. So I've found myself just wanting to make sure you can at least read the book. So that's your radius. That's the circle that you're on right there. But, then you cruise on a little further, and then you kind of take this super sharp corner over here. So there's another location. So let's say you're right here. Would you agree that's a much tighter circle? So maybe the center would be there. And so then you'd be kind of at this radius, much smaller. And so what are the considerations of these? Well, here's the thing you need to understand about this kind of motion. Well, would you agree this is the direction you're traveling? Perpendicular, it'll always be perpendicular to that. That's the direction of travel. That would be both velocity tangent and acceleration tangent. In other words, if you look down at your speedometer and as Daniel pointed out, you're going 50 miles an hour, that's your vertical velocity, I'm sorry, your tangential velocity. But in this direction, something also is happening, and that is this. That's your not tangential acceleration. So A of t is tangential. Or just tangent acceleration. And again, that's just typical acceleration. Like if you push the pedal, you push the pedal and go faster. This is, if you will, a speed. This is what you always think of as acceleration. It's just a speed change. I'm changing speed. So I'm in there and I'm not on cruise control. So if you were on cruise control, the length of that would be nothing. There'd be no length there at all. But in this direction, this is called a N. which is normal acceleration. What's the word normal mean in physics and advanced math?
Perpendicular.
Perpendicular. It's just another word for perpendicular. So it's always perpendicular. This is actually not a speed change at all. It's a direction change. From physics, what's your understanding of that, if anything? What's another name for that? That's kind of, what's the common name for that? Common name for that is centripetal acceleration, which is why you sort of smash against the door. Does that make sense? So if you turn your car to the left, or let's say you're in the passenger seat, you're sitting there and the door's on your right, and somebody turns the car to the left, you kind of smash over against the wall. That's the car, like, you know, pushing you to change your direction. If you're in a car and you're going down the road straight, your body wants to fly straight. If your car turns left, your body still wants to go straight. So the car starts pushing on you. What's it doing? Well, it's pushing you toward the center of the circle that you are going around at that moment in time. So that's changing your direction. It's a direction change. So tangential acceleration is a speed change. Normal acceleration is a direction change. And therefore, your actual, and your assignment will ask you this some, but your actual acceleration is those two vectors put together, since those are technically vectors. So maybe I'll add over here, if VT was, or if AT was going this direction and you moved them head to tail so that AN was going this direction, then your actual overall acceleration. I don't like questions that actually ask you for just the acceleration. If your problem asks you for acceleration, it wants you to find both AN and AT and then do Pythagorean theorem on them. So that's like the combination then. It's the combination of your speed change and your direction change. It just feels like when you put those together, it's sort of lost as to what they mean. I kind of like leaving them apart. I wish the problems only asked you specifically what's your tangential acceleration. In other words, how the longer that vector is, the kind of the faster you're turning a corner. That's kind of the idea. The bigger that number is, that means the harder you're turning. Well, again, let's just to see it in a different context, let's look at the other one. So if you're traveling along this, then isn't this your tangential acceleration? And by the way, that could be backwards. In both cases, it was forwards, which means you're speeding up. But the black one was a little longer, so that means you were speeding up more in your black location than you were in the green location. And this would be your A of N, and again, those are going to be perpendicular. So if I was to be a little more careful about this, since this wasn't that sharp of a corner over here, does it make sense that this one would technically be shorter? Just in terms of your understanding of it? Because it's not, you're not getting slammed against the door as much. You see what I'm saying there? So AN is not going to be very long. It's not a very big number when you're not turning very sharply. It's going to be a much bigger number if you're turning sharper, which is why I drew this one a little bit longer over here. So they act totally independent of each other. Does that make sense? One is I'm pushing the gas pedal. The other is I'm turning the steering wheel. You with me there? I'll write that. Gas pedal. Steering wheel. So AN is an interesting acceleration because it's not actually a speed change at all. It has nothing to do with speed change. So the two formulas that are on my formula sheet that you need to know to solve the problems in this section. And we'll go do an example in just a second. But one of them I already mentioned to you, that the rho radius is 1 plus the derivative of the equation squared, all raised to the 1.5 power divided by the second derivative. And the second formula is that acceleration normal can be found if you know the velocity and the radius. You divide them after squaring the velocity. Now, let me ask you a question. I want all three of you to answer this. Do you care where those formulas come from? Evel, do you care?
Well, I'm understanding the first formula, where it came from, because we talk about that. I'm still not really sure about the second formula, but yes.
You do care. Okay, Landon,
Yeah, I'm curious.
curious. Daniel,
I'm curious, but I won't lose any sleep over not knowing.
fair enough. So here's what I'm going to do. I'm teaching this class, of course, I might get asked this question, but I'm just a curious person, and I've taught it more than once, but I'm just going to show you these quickly. I'm not going to give you time to understand them because it'll take an hour to understand these, but I'm at least going to show you. So I made my own page that explains where this formula comes from. So there's the rho formula, curvature. And I really would encourage you to go look at these a little bit. You might just look at them a hair, or you might look at them a lot, but I'm bothered by stuff like this until I understand where it comes from. And so as you see, there's a bunch of algebra and calculus, and the end result is, bing, there's the formula at the bottom. So I'm going to post that. And this is my own creation because I find myself looking at books and not really able to tackle it. So I explained it here as simply as I possibly could. And unfortunately, the other one's even worse. I haven't even made this one nice. Actually, I thought I had, but maybe I lost it. I don't know. The normal acceleration formula. So I just wrote this out by hand. So in the end, down here at the bottom, you have vector A equal to V squared over rho. I mean, you have kind of that final formula. This is sitting in your book. If I remember right, it's on page, I'm looking at my notes here, on page 56 and 57. And I found it real. I mean, I had to spend a lot of time with this to make sense of it. I really did. Like I was not tracking with this. And even looking at what I did, notice there's like 1, 2, 3, 4, 5 steps there, if you will. Even when I made this last year, but even when I looked at it today again, I thought, man, that's not easy. Like I had to figure it out. But the gist of it has to do with, if I'm sitting here at this point right here, and I have, that's my direction of travel, and this is aiming toward the center, and then a little time passes, and now I'm here. Now this is my direction of travel, and as long as this angle is really small, both of these lengths are still r, or rho for radius. It has to do with playing with that picture and the fact that there's a relationship between this arc length, that radius, and this angle up here. So anyway, I'll let you think about that. We can talk about that outside of class if you want to. What I want to get to right now is just at least an example of how to get the dumb problem right, how to get a problem right using those beautiful things. And so let's take a look at one. Again, what I think is kind of interesting about these questions is they're pretty contrived. And this is a classic physics example because you have a box sliding down a ramp, and you know, for this class, I'm going to be replacing that box with a skier, you know, and things of that nature a whole lot more just because I find that interesting. I find it like, I feel like it's worth studying if I look into that. So fine, think of it as a skier. So notice the other thing that's contrived about this is what's the shape of the ramp it's on?
A parabola.
It's parabola. Like why would the ramp be a parabola? Now, can somebody design one to be a parabola? Sure. But you know, in the real world, if I go out skiing and I'm going down a ramp like this, it's not a parabola. It's just some dude on a snowcat, you know, dragging until it was curved, right? It's a curve. Like who knows what the equation is? You should understand from math that if you wanted to take pictures of this from the side and plot some points and do regression, that you could actually make an equation out of something that somebody did entirely randomly. Do you agree with that? So you could do this even if there was no equation. But I say contrived because, you know, when is this really going to be a parabola? Now, fortunately, derivatives of parabolas, because remember, we're going to have to take the derivative. That's a really nice derivative. Like I don't want some terrible equation like y equals x sine of x, and the derivative of that is the product rule. And it's like, oh my gosh. So, you know, this is not supposed to be a calculus class. You have to know calculus to be in it. But anyway, what is this? So why does it say the box of negligible size? Why would you say that? That's a weird statement.
Probably so you can treat it more like a point particle.
Yeah, so you can treat it like a particle. In other words, they don't want us to get confused about the fact that the box is like 6 feet long or something. And so then it's like, where is this thing? So they're just saying, treat it like a dot. And so it's traveling down this parabola. When it's at A, and it tells us where that is, it's at the point 2, 1.6. So I know the coordinates of the point it's at. That's the point they're asking me something about. And of course, that you always have to know where you are, because where you are determines that circle that we were talking about. So even though this is a parabola, we're on a circle. At that point, we're on a circle, right? At least for that second or so, at least for just the time right around that location right there, at least from, you know, here to here, at least from there to there, we're on a circle. Now notice that circle's got a pretty big radius because that's almost straight right there, right? And so we say, well, we'd like to find stuff out about that. So we know we're at the point 2, 1.6. Everything is metric here. I don't know if I care about that, but they told me it was metric. So I'm at the point 2, 1.6. And let's see, what can I know? Well, can I know the radius of the circle? Can I know that radius? Well, our formula was 1 plus the derivative. What's the derivative of 0.4x squared? Y'all tell me. Your calculus teacher wasn't that bad, was it? Was she or he?
My calc teacher was you, so you can be the judge of that.
I know. You guys are throwing me under the bus here. All of your calculus teachers were mean. What's the power rule say? Since this is just a parabola, I take that exponent of 2, multiply it down front so it becomes 0.8, and then that x to the 2 becomes x to the 1. So there's my first derivative. And I know what that is at the point x is 2. Notice that only calls for x. My derivative only calls for x. So it's 1 plus the derivative squared. This is the formula. I'm hoping you're looking at your formula sheet, so you're getting used to looking at that thing. 1 plus the derivative squared, and all of that is raised to the 1.5 power, all divided by the second derivative, not squared or anything, just the second derivative. And you might notice on your note sheet that says absolute value, which means no matter what the sign is, make it positive. So let's see, what's the second derivative of what's the first derivative is 0.8x. The second derivative, also according to the power rule, is just 0.8. So it's a constant. I don't even have to plug anything in. It's just 0.8. Cool. Again, I'm just figuring out things that I can figure out. I haven't even really read the question yet. I'm just wondering, can I find that? I'm probably going to need it, but so when I punch all that in at x is 2, I get that the radius is approximately 8.396 because we're talking about metric here. That's meters. And I'm just putting a little cloud around it saying, hey, that's an important calculation. All the other stuff led up to it. But in a sense, I could erase everything I just did. And this is the important takeaway. And so that's kind of cool that I actually literally know the radius of them. Isn't that amazing? That's really cool to think about. I literally know the radius of the circle at that point right there, even though I'm on a parabola. Really cool. They tell me the speed at that point is 8 meters per second. Velocity can only be tangent. Like that's literally your speed change. So I'm given that. And do you understand it said when it's at A? Does it make sense if you're sliding down a hill because of gravity, your speed's changing? So it's not going to be 8 a second from now. And of course, again, very contrived, like 8. Okay, where did that come from? God told me, I guess. And where did it come from? The problem told me. So I know the speed at that point and the increase in speed. I also know that. So I know that velocity, and I'm even going to say at point A, just because it's kind of cool to understand that it's going to change. But then I'm told dv dt is the increase in speed. What's that code for, the increase in speed?
Acceleration?
dv dt, yeah, that's acceleration. Now, what we learned today, though, is there's 2 types of acceleration. There's normal and tangential. Which one is this?
Normal? Or sorry, yeah, normal.
Why? Like, how do we know? Is Landon right or wrong? What do you think? So this is an increase in speed. They call it dv dt. And they tell us it's 4.
Is that tangential because it goes almost in the same direction as the actual speed because it helps it accelerate?
So this literally is, where did that go? This goes back to, was it here? This goes back to these 2 definitions right here. They said dv dt, that's a change in velocity.
Shoot.
It's tangential acceleration because they told us you are changing velocities, not changing directions. Does that make sense? So because they said dv dt, they're saying you're literally changing velocities. They're saying it's 8, but it's changing and getting bigger. And of course it'd be getting bigger because I'm sliding down a pipe, right? My speed's increasing and increasing. So they're telling me a speed change by saying dv dt. Normal acceleration is a direction change, not a speed change. So it is not obvious, but that is actually tangential. I'm gonna change colors. Boom, so it stands out. And I'm going to make a note here. This is a change of velocity or speed. Because of that, it's acceleration tangent. So I know the tangential acceleration. Again, how do I know it? Well, somebody just told me. Later chapters will go into, well, how does gravity going to change that? If a skier takes off the top of a hill and just starts sliding down, you figure out his velocity and acceleration. Like, you don't have to be told this from nowhere. We're just given these things. Again, I haven't even read the question yet. I don't even know what they're asking. I'm just writing down stuff that they're telling me. Finally, I get to the question: determine the magnitude of the acceleration of the box at this instant. So now I'm thinking, I found the radius for nothing. I found rho for nothing. Because they didn't even ask me for that. But they said, determine the magnitude of the acceleration of the box at this instant. Well, didn't they just tell that to me? It's 4. Well, remember what they're asking me for here is they're asking me for this. They want the acceleration. They didn't say tangential. They didn't say normal. They said, what's the acceleration? So in order to know that, because of the Pythagorean theorem, I have to know acceleration tangential. Oh, I know that. That was 4. But I'm going to have to know acceleration normal too. I don't know that. I'm going to have to figure that out. So how do I get acceleration? Whoa. How do I get acceleration normal? Well, we have a formula for that too. That was v squared over rho. So I did need rho. That worked out good. So in our case, we knew the velocity at A, it was 8. And we calculated rho, it was 8.396. And so the fact that I just figured some stuff out, I ended up needing all those things. And so I'm about to know what the normal acceleration is. And that turns out to be approximately 7.62 feet per second squared. And so I have that normal acceleration, and I have the given tangential acceleration. So with respect to this picture then, because I'm sort of right here, if you will, I have my tangential acceleration of 4, and I have my normal acceleration that's almost double that of 7.62. And they want ... If I replace this, they want the actual acceleration. Does that make sense? Thank you. So do you see that as a Pythagorean theorem question? That's what they want. So A is 4 squared plus 7.62 squared square rooted, which works out to be about 8.6. I said feet back here earlier, but everything we measured in was not feet, it was in meters. So meters per second squared. So that's a combination of both tangential and normal. So basically I found its total acceleration. Again, as I said before, I think, although fine, that's the question, that's the answer in the back of the book, and I got the problem right. I would prefer to just keep these separate if you left me alone, but because now I understand 7.62 kind of tells me how curved, that's curvature. It kind of tells me how curved the circle is that I'm on. So how sharp the turn is. Does it make sense? A small radius has a really sharp, that's a sharp turn, and a huge radius is a really gradual turn. So I'd rather keep these separate because they are talking about totally different things. It almost feels stupid to me, and I'm probably wrong about this because I'm not a physics major, but it feels kind of dumb to me to collect them together somehow into one acceleration, because now I've combined a speed change with a direction change. It just seems like, why would I do that? I would like to have Wow, Daniel's gone. Happy birthday, Daniel. I'd like to do another example, but it's 12:20. So the only thing I will say, just out of we only did 2 examples here in explaining all of these things, but I have a note to myself. I haven't looked at this in a while, but I have a note to myself that says that question 141. There's only 2 questions, if I remember right. There's only 2 questions in 12.7. So I just did what I'd consider to be a nice, fairly easy, straightforward one, something like you might see on a test. But I have a note to myself that question 141 is a challenging one. So let me see. I just want to see if I can stare at that and see if there's anything. I guess I'll just write this in here. I have a couple of hints here written to myself, but I don't, because I didn't even look at the question at a time. I'm not even sure what they pertain to, but I'll just say this. Question 141, hints 1.
Oops, I cropped that improperly. Hold on. I can post a picture of it.
Yeah, take a look at it if you have your book or something.
That's correct.
The question I just did was a little more straightforward, but since that formula tells us if you know the velocity and the radius, you can use those to find the normal acceleration. Does it make sense that this can be used for other things? In other words, it can be used to find rho. Like if you knew the velocity and the normal acceleration, does it make sense you could use that to find rho? Use the equation for a different purpose. It's really an equation with 3 unknowns. So if you know any 2, you should be able to find the third. So I have that hint written down. And then the second hint I have written down is to find theta at the LZ, which I think means landing zone, like where you land. Let me start question 2. I'll just pull it up since Landon. Oh yeah, okay, there we go. So I just pulled up what Landon sent and shared it with you guys. And so, yeah, this is an awesome problem. It really is kind of a cool problem. I've thrown snowballs out of my car window, as I'm driving, for instance, to try to hit signs. And
Okay, I have to go to work.
yeah, off you go. So you use those 2 hints. We can talk about it a little bit more later, but yeah, we got to get out of here. So, all right, y'all have a good day. I'll post all this and we'll talk more next week.
Cool.
All right.
Thanks.
Thank you guys. Have a good day.
Yep, you too. Bye.
Hey, Doug. Oh, actually, before you
Yeah.
go,
Good.
first midterm,
Yeah.
I completely spaced on it and thought I just took care of it relatively earlier in last term. So
Yeah. Let's see, what did I email you about that? I said, if you take that and do reasonably well, you'll pass the class. Is that what I said? That sounds like what I said.
yeah, I did the math on it.
Got it. So I would want you to do that relatively soon, just because then I can go in and change your grade from last term. So when are you free in the next few days so that I can to you?
Let's see. This afternoon, all of tomorrow. I don't really have a lot going on right now, so
Okay. Why don't I email it to you today, and then you take it. I'll tell you in the email how much. I forgot how much time I gave everybody to take it last term, but I'll just tell you that much time, and you can take it anytime you want and get it to me by tomorrow evening or something.
all right.
That's unfair.
Yeah,
Okay, making myself a note. All right, I'll handle that pretty quick.
all right.
See you, my friend. Have a good day.
See you, Doug.
Bye-bye.
Bye.